So this is a joint work with Eugenia Ternovska, who will give another presentation about the logic of information flows later, and some colleagues from the UHasselt. So I will start by giving you the conclusion of the paper so that you know what we're working towards. So what we present here is in the context of the logic of information flows, which is roughly first order logic, but given a dynamic semantics to describe composition of modules that do some type of computations. And with this dynamic semantics also comes an extra operator, namely composition. We tackle two questions in this work. The first one is, this logic of information flows, inputs and outputs are very important for it. It starts by adding inputs and outputs to a language. And the first question we answer is, what does it actually mean to be an input or an output of a live expression? So it goes to the heart of the logic. And we give a semantic and a syntactic definition of it. And the second question we ask is, well, it's first order logic with an extra operator. Is this composition, this extra operator actually needed, or is it primitive in the logic or not? And we give positive and negative results. So the logic of information flow, it's a knowledge representation formalism to model how to combine different atomic building blocks into a complex dynamic system. And a module or a building block there is roughly a relation that has input arguments assigned to it and output arguments. I'll give an example on the next slide. And connecting these building blocks happens with the usual first order logic. In some settings, like Eugenia will present probably in the higher order setting, maybe with fixed point logic. So there are extensions, but in this talk, it's roughly first order logic. So a very small example, suppose we have a binary relation increment, and I assume that D here is some instance, some interpretation in which this binary relation consists of all tuples, natural number, and natural number plus one. So it just means that the second is one higher than the first. The standard static semantics is what you see here. That's the standard static semantics of first order logic. The dynamic semantics that logic of information flow gives to it is this one here, in which we say that a tuple of two valuations satisfies this increment xy if, and now it's important to notice this here, this colon here, it means that the y is an output and the x is an input. So the first argument is an input, the second argument is an output. So, and the semantics then means that the value of y should be one higher. So this one higher comes from the interpretation of increment in D here. The value of y after executing the module should be one higher than the value of x before executing it. So this new one refers to, it interprets the variables before executing this module, and this new two interprets the variables after executing it. You can also have that you have two times the same variable in there as input and as output. In that case, it really means this atomic module here really increments the value of x by one. So it's satisfied by tuples of valuations in which nu one of x is one higher than nu two of x is one higher than nu one of x, and everywhere else the valuation is unchanged. So there's a law of inertia going on there, and so a set of such couples of valuations, we call it a binary relation on valuations. Now, how can these building blocks be combined in LIF? Well, with the standard Boolean connectives, there's selection, there's projection, we call it a bit differently, and there's a special operator composition, which does exactly what you think it does. Sequential composition, it means first execute R and then execute S. So its semantics is given by all couples of nu1, nu3, such that there is some intermediate nu2 that you can reach in R and from which you can reach nu3 using S. One thing important to notice is that selection and then existential quantification / projection, we call it cylindrification because of a link to cylindric set algebras, is also given some dynamics in the sense that here we, for instance, say that we're doing selection on the left. You can similarly do selection on the right. I will not go too much into details there. I will let you read the paper for that. So question one, this logic of information flow, it really starts from, you have relations, let's assign input and outputs to them, arguments, and let's see how the information flows through dynamic systems using these inputs and outputs. But so far, it was unknown what would be inputs and outputs of compound expressions. So if you combine them, which variables would you meaningfully be able to call an output, and which ones should you call an input, or which ones are none of these? And that's our first question of this that we tackle in this paper. So yeah, here's an example. I will skip it because I just heard that I have 3 fewer minutes than I thought. So here's our definition of outputs. At the atomic level, everything that's not an output is preserved by inertia. So we just propose as a semantic definition of outputs to use the set of variables that are not necessarily inertial. These are called outputs. Why is this? Because all these dynamic systems can do, the only thing they can do is change the valuation. Yeah? So their effect on the world, their perceived output can only be seen in the variables that they change, the variables that they touch. So intuitively, what we call a semantic output is a variable that can be changed by this expression. And this corresponds exactly to the outputs of an atomic module. The intuition behind inputs is that, well, our first intuition was, well, inputs are those variables that you need in order to determine what the valuation is that will come out after executing the module. But in general, that would mean that all variables are input, because most variables, all the ones that are not mentioned, are inertial. If you want to know which valuation will come out, will exist after executing the module, you need to know all the inertial variables as value at the beginning, and that would not be a real meaningful definition. So our definition of input, it's almost what I said before, except that it's those variables whose value you need to know in order to determine what the value after executing the module will be, but only on the outputs. Because everywhere else, you know, it's inertial anyway. So it's the variables you need to determine the outcome on the outputs. These are the inputs. And we have some nice semantic definitions, but of course, they bring us into problems. Namely, the problem deciding is a variable a semantic input or a semantic output is an undecidable problem. So this well, forces us to take a step back and to think, okay, can we come up with other definitions, syntactic approximations of this type of these inputs and these outputs? And we did that, and we came up with this definition. I think if you look a minute at it, you'll see that it's perfectly correct, that these are exactly what should be inputs and outputs. I'm just kidding, of course. If I would see this definition in the paper, I would at first be horrified, and in second instance, I would get very suspicious, because it seems like too many case distinctions that are made there to make some example work or something. But we have a good reason for taking this definition. I will not tell you the details of the definition, but only the properties why we claim this is a good definition. And these are the following. First of all, the proposal we have is sound. What does it mean? The syntactic outputs, they contain all the semantic outputs. And secondly, the syntactic inputs are enough to determine the behavior of the module on the syntactic outputs. So there is some notion of input-output determinacy. And from these two conditions, it also immediately follows that the syntactic inputs contain all the semantic inputs. So this is a soundness that we would need, that I think that any reasonable syntactic definition of inputs and outputs would have to satisfy. And the second property is compositionality. Namely, the inputs and the outputs of a complex expression only depend on the inputs and the outputs of their direct sub-expressions. So it means that this definition follows the structure of the syntax of the language. And moreover, the reason why we have all these different case distinctions in our definition is optimality. Namely, our definition, we proved that it's the most precise compositional and sound definition that can exist. So if you have something that's compositional and sound, it's as precise as our definition. Just a very small example where syntactic and semantic outputs can differ. If you have this expression here, you have some module R with input X, output Y, and then you do a selection on the left and on the right of X equal to Y. What this means is that you will only allow inputs in which X and Y are equal at the beginning and are equal at the end after execution. Now, since X is inertial, the combination of these two operators means that y will also be inertial. It cannot change value because it has to be equal to x before execution and after execution. So this forces y to be inertial. Still, our syntactic definition does not capture this. And because of our optimality, it means that you cannot figure this out by reasoning on this as being a black box. That's roughly what this means. So that's the first question. What are inputs and outputs? We now have a semantic and a syntactic answer. And the second question is, well, this composition that you add to the logic, do you need it, yes or no? And we have answers that claim you don't need it. So suppose our expression, our composition alpha, first execute alpha, then beta, has the property that beta is well behaved. And well behaved here means it doesn't override variables that it needs to determine its outputs. So the inputs and the outputs of beta are disjoint. In that case, we can show that we can rewrite this composition into this expression here. Now, a second case that says that we don't really need composition is, suppose you have an infinite set of variables, and you can always get rid of your compositions. And the trick is roughly that you use these unused variables, you have plenty of spare variables, you use them to force your expressions to become input-output disjoint by moving variables around a bit, by enforcing an expression instead of to write a new value over one of its inputs, to write it in a new variable, and then you have to be careful a bit. But that's the essence of our proof. But then we also have a primitivity result, namely, if you only have a finite set of variables, then composition is primitive. And the intuition, the proof roughly goes like this. First, we show that if you have n variables in LIF, you can express the existence of a 3n click in a graph. And secondly, we show that without composition, with only n variables in LIF, you can translate this into FO2n. So in which we know that 3n clicks cannot be discovered. So some related work. We use these inputs and outputs also to study how LIF relates to executable first order logic to query under limited access patterns. Dynamic predicate logic might be something to investigate as future work, because their semantics is defined quite similarly, also with pairs of valuations, but there's some different in the intuitions behind the language. And we think that inputs and outputs might be useful for problem decomposition. If you know that a certain module will not override certain values, you can parallelize, or you can decompose your problem better. And there are other operations sometimes considered in LIF that remain to be investigated, but the principles of inputs and outputs will remain the same. So thank you. We've seen this slide already, so I would be happy to answer questions.